Hello friends, how are you today? So, in the previous lecture, that is yesterday, we discussed about the fundamentals of conduction, and in this week we are looking to continue on that, that is the Fourier's law of heat conduction that we have discussed. I am going to develop on that, and today we are going to discuss about the heat diffusion equation in Cartesian coordinates. Now, just to review the discussion on Fourier's law of heat conduction that we had in the first lecture, there we have seen that though we started with a very basic one dimensional kind of form of Fourier's law of heat conduction, but the most generalized representation of Fourier's law of heat conduction is the conduction heat flux can be written as minus k into dou t dou n, where this n cap represents the direction of normal to the surface where we are talking about, and dou t dou n represents the temperature gradient in that particular direction. Or more general representation can be minus k grad t, where this grad t is the temperature gradient which can have all three possible coordinates. Like if we write in Cartesian coordinates, this is dou t dou x I plus dou t dou y j plus dou t dou z k. Quite often we write this one as something like q dot the x component of heat flux plus the y component of heat flux plus the z component of heat flux, where the x component corresponds to just the concerned temperature gradient, that is q dot x double prime will be just dou t dou x, q dot y double prime will be dou t dou y, and q dot z double prime will be equal to dou t dou z. So, these are the three components of heat fluxes which we can find, and once we know the orientation of a particular surface, that is once we know the direction of the normal of a particular surface, then we can estimate the temperature gradient in each of the three directions and then combine to get the expression for this temperature gradient, and multiplying that by the thermal conductivity, we can get the expression for the corresponding conductive heat flux. Actually, the heat flux expressions that I have written, they are incomplete, because all of them should be multiplied with the thermal conductivity, and if we are talking about a non-isotropic material, then the magnitude of thermal conductivity can also vary in all three possible directions. And also another property that was introduced in the previous lecture and that will come back today, that is the thermal diffusivity or alpha, which is defined as the ratio of thermal conductivity and volumetric heat capacity, that is rho into Cp. With this background of Fourier's law of heat conduction, let us try to develop something known as the heat diffusion equation. In this heat diffusion equation, I should make it very clear at the beginning that we are neglecting any kind of convective or radiative heat transfer. Just assume that, say, we are talking about the situation inside a solid, like this block shown here. We have a solid block. Just for the moment we assume that this is solid block, though the same situation prevails in liquid and gases also, but just for ease of visualization we are assuming this one to be a solid block, and we are talking about a point inside the block, and we want to know the conductive heat fluxes that is acting on this block in all the three directions. These are the coordinate directions x, y and z. We want to calculate the conductive heat fluxes that is acting at this particular point in all three directions, and also we want to know the temperature distribution inside this body because of this conduction heat transfer. So, T is the temperature, T x y z represents the temperature at this x y z location, and we have a zoomed view of this. Just assume that around that point we are assuming an infinitesimally small volume, just shown here. It is an infinitesimally small volume which is having dimensions as dx in the, or the value of the phase length in the x direction aligned with the x coordinate is dx, the one aligned with the y coordinate is dy, and the one aligned with the z direction or z coordinate is dz. Q dot x or qx, or though the I have taken this particular diagram from the book of Incorporated and Dept, where they have not put the dot notations, but for our convenience or just to be consistent with our notation, let me put the dot here. This q dot x represents the conduction heat flux which is going in the x direction and is entering this block from the phase that is shown. Just the opposite block of that, or opposite face of that block through which this q dot x plus dx heat flux that is going out. Similarly, through the plane which is aligned with the x z direction, that is it is having q dot y amount of heat flux entering through this side and q dot y plus dy leaving the block from that side, and considering the two faces which are parallel to the x y plane. So, this is q dot z heat flux, that is heat, not heat flux, that is the heat transfer rate, conduction heat transfer rate passing through the passing into the block and aligned to the z direction. This is q dot z plus dz, this entering through this. We are assuming this block to be infinitesimally small, so that each of the faces are also very small, and therefore, we are considering the heat transfer through them, through conduction heat transfer through each of them only by the corresponding normal components. Now, that q dot x plus dx which is leaving to this side, dx being extremely small, we can expand this one following Taylor series. If we expand this one following Taylor series, what we can write? Let us just write in a conventional functional form, q dot at x plus dx. So, this should be q dot x plus dq dot dx into dx plus the second order terms. I should write this in partial differential notations, plus dou 2 q dot x dou x 2 dx whole square by factorial 2 plus the other terms. So, if we neglect the terms from second order onwards, assuming dx to be extremely small, then this one approximately is q dot x plus dou q dot x dou x to dx. Just the same we can write q dot y plus dy, that is the conduction heat flux which is leaving through this particular phase. This can also approximately be represented as q dot y plus dou q dot y dou y dy, and q dot z plus dz can approximately be represented as q dot z plus dou q dot z dou z dz. Now, just look at, there are two more terms that is shown on this figure. Here this E dot g represents the rate of energy generation inside this block per unit volume. So, rate of, I should write thermal energy generation inside the domain of our consideration per unit volume. Similarly, the other term that is shown here, E dot St, that represents the rate of thermal energy storage inside the domain, or maybe inside the control volume, just to be consistent with the thermodynamic notation, per unit volume. Because you can see there are 6 different heat transfer rates that we are considering. As per the diagram shown here, 3 of them are entering the block, 3 of them are leaving the block, and also there is an energy generation which can be present in certain limited cases. Like suppose if this block we are talking about is made of some kind of nuclear fissionable material and some nuclear reaction is going on, then definitely some energy will be generated, the energy released by fission reaction will be converted to thermal energy. Similarly, all these 6 incoming and outgoing heat transfer rates plus the energy generation together, if they are not properly balanced, then that will lead to a net increase or decrease in the total energy content of the block itself, that is given by this second term. Now, if we write an energy balance over this particular block, then let us do one thing before writing this. Let us remove this per unit volume term. E dot g for the moment because that is the more convenient notation, E dot general represents the rate of thermal energy generation inside the domain. We should have put that triple primes notation to make it per unit volume. Let us use some other notation. Then what will be E dot G in that case? Then E dot G will be just the volumetric rate. Q dot G triple prime is nothing but per unit volume of the same quantity. Then the total rate of thermal energy generation will be how much? This Q dot G triple prime multiplied by the volume of the block dx dy dz. And what will be the rate of thermal energy storage? How can we estimate this one? That just from energy balance, what we can write this? This should be equal to the total mass of the block, that is rho into the volume, where rho represents the density. So, this is the mass of the block into its specific heat into the time rate of change of its temperature. So, from there, or I should not write this because t is a function of all three coordinates, because here t is a function of time and x, y and z. So, at this particular location, whatever is the time rate of change of temperature, that multiplied by the mass of the block into the specific heat of the block given by this C, that gives you the rate of energy stored inside this because of the conduction heat transfer. I repeat again, we are neglecting any convective or radiative heat transfer. So, only conduction heat transfer that we are talking about, and so this is the rate of energy storage. So, now if we write an energy balance over this, what we can write? Following the first law of thermodynamics for a control volume, we can easily write that the rate of energy coming in minus rate of energy going out plus rate of energy generation has to be equal to rate of energy storage. For this, if the three quantities on left hand side are properly balancing each other, then the right hand side will be 0, that is there will be no change in the net energy content of this. Now, if we write their expression, then what are the forms energy is coming in? So, E dot in, as we can see from the diagram, energy is coming in as q dot x plus q dot y plus q dot z. These are the energies coming in, minus energy going out of this is q dot x plus dx plus q dot y plus dy, q dot z plus dz plus energy generation. So, as per our notation, that becomes q g triple prime, that is volumetric rate of energy generation into the volume dx dy dz, that should be equal to the rate of energy storage, which we have written earlier, rho, let us take this C together, into the volume into the time rate of change of temperature. Now, if we put the expressions for the three components that we wrote in the previous slide, that is these three expressions, then we have on the left hand side q dot x plus q dot y plus q dot z minus q dot x plus dou q dot x dou x dx plus, this is for the q dot x plus dx, q dot y plus dy becomes q dot y plus dou q dot y dou y dy minus q dot z plus dz becomes q dot z plus dou q dot z dou z dz, and that is equal to the two terms, they remain as it is dx dy dz. Sorry, this should be plus sign, this is equal to rho into C into dx dy dz into dou t dou t. So, if we balance them together, then we have minus dou q dot x dou x dx plus dou q dot y dou y dy plus dou q dot z dou z dz plus again that q 0 triple prime dx dy dz is equal to rho into C into dx dy dz into dou T dou T. So, here we have done an energy balance over this infinitesimally small control volume that we are considering, subjected only to conduction heat transfer, and from there we have got some intermediate expression. Now, look at the three heat fluxes that are given to us. The three heat fluxes that we have now, we have q dot x, or I should say dou q dot x dou x we have, but what is q dot x? Just look at this diagram again. This is our q dot x, which is energy entering this block through this particular phase via conduction only. Then using the Fourier's law of heat conduction, what we can write? This should be equal to the corresponding conduction heat flux acting going in the x direction into the area of the plane having normal in the x direction. Here Ax represents the area which is having normal in the x direction. Now, using the conduction equation, what is the first term in the bracket? The heat flux using Fourier's law of heat conduction, that is minus Kx dou T dou x, and what is your Ax? What is the area of, or what is value of this area through that this particular area that I am talking about? This is the one I am talking about. It is the area which is aligned to the yz plane and having normal in the x direction. So, its dimension will be dy dz. So, this area is dy dz. So, this becomes minus kx dou T dou x into dy dz. Similarly, q dot y should be equal to the conduction heat flux acting in the y direction into the area having normal in the y direction. Using Fourier's law of heat conduction, this is minus ky dou T dou y, and which area now we should put? We are talking about the area which is having normal in the y direction, that is aligned in the xz plane. So, that is nothing but dx dz. So, it is equal to minus ky dou T dou y dx dz. Similarly, q dot z should be equal to the conduction heat flux acting in the z direction into the area having normal in the z direction. So, the first term using Fourier's law of heat conduction is kz dou T dou z into area Az, the one having normal in the z direction, that is aligned with the xy plane. So, this is nothing but dx dy equal to minus kz dou z dx dy. Now, let us put these expressions back here. So, if we put these expressions here, then what we are having? So, we have minus dou x of q dot x dx. So, from here we have to get minus dou x of q dot x dx, from where to put this one. So, if we write this, then we have minus dou x of minus kx dou T dou x into dy dz into dx outside. So, this goes the first term. The second term we have to put in this. Look at what we have, minus of dou q dot y dou y dy. So, we have to put it in minus of dou y of q dot y dy. So, we have minus dou, let me separate this one out, minus dou y of minus ky dou T dou y dx dz into dy. Similarly, the last term can be written as dou z of minus kz dou T dou z dx dy into dz. So, these are the three terms. Then the remaining two terms, that is the energy generation and the storage, remains as it is. So, that becomes qg dot triple prime dx dy dz is equal to rho c into the volume, that is dx dy dz into the time rate of temperature variation. Now, if we assume this, as we are assuming this block to be infinitesimally small, then these dimensions dx, dy and dz all can be assumed to be independent of each other. Particularly if we are talking about a rigid block, then these dimensions are not changing and they are all independent of each other, that is this dx, dy, dz can come out of the corresponding differentials. Then in that case, also taking the minus signs out of this, we are getting dou x of kx dou t dou x into dx dy dz plus dou y of ky dou t dou y dx dy dz plus dou z of kz dou t dou z to dx dy dz plus qg dot triple prime, that is volumetric rate of energy heat generation, into dx dy dz is equal to rho into c to dx dy dz dou t dou t. So, dx dy dz represents the volume of this particular block that you are talking about, and that can be cancelled out from this. So, we are getting the equation now as dou x of kx dou t dou x plus dou y of ky dou t dou y dou z of kz dou t dou z plus qg triple prime is equal to rho c into dou t dou t. And this particular one can be considered as the generalized form of the heat diffusion equation, where of course, we have neglected in this equation dV represents the dx dy dz, that is the volume of this infinitesimal block, which cancels out. So, if we write it again, the most general form of the heat diffusion equation comes to be dou x of kx dou t dou x plus dou y of ky dou t dou y dou z of kz dou t dou z is equal to rho c dou t dou t. So, this is the generalized form of the heat diffusion equation or generalized form of the heat conduction equation, where we have of course used the Fourier's law of heat conduction, and we have neglected any kind of convective or radiative heat transfers, but we have not put any other assumptions of course. Nothing else has been assumed so far apart from the absence of any kind of convective and radiative heat transfers. Now, what kind of equation is this? This equation you can see it is a partial differential equation which has both space and time dependencies. It is a 3-dimensional equation. The kx, ky and kz are the 3 components of the thermal conductivity. For non-isotropic medium, only for isotropic cases they become equal to each other. This and also one thing we have to remember, that the equation that we have written, that is in Cartesian coordinate system. So, most of the system that we deal with, they are generally Cartesian in nature, or we can use a Cartesian coordinate system. So, this equation can always be used there. In certain cases we may have to go for cylindrical coordinate, or even limited number of cases we have to go for spherical coordinate system, and these two we shall be discussing in the next lecture, when again I shall be developing the generalized heat diffusion equation for both of them. But for the moment, just continue with this heat diffusion equation in the Cartesian coordinates. So, look at what terms we are getting. The first term that we have, dou x of kx dou t dou x. From where we have got this one? Just if we just retrace back the way we have derived this, neglecting the area part, then this basically is the heat flux q dot x double prime, the conduction heat flux, of course I am not writing conduction. It is this quantity only, the amount of conduction heat flux that entered the block from one side, that is the amount of conduction heat transfer that entered from this side minus the conduction heat flux that is leaving through this particular phase, that difference is given by the first term. Similarly, the second term, actually I have missed something. Okay. While writing the final term, I should have the Qg. Sorry if any of you are confused, because that was a mistake while writing this. Now, the first term therefore represents the net conduction flux. Similarly, the second term represents the net conduction flux acting through the two phases having normal in the y direction. Similarly, the third term represents this term, the net conduction flux that is entering the block through the areas having normal in the z direction. Then we have a volumetric heat generation, and these four together, three fluxes plus the volumetric energy generation together, they give you the time rate of change of energy storage inside this block. Now, there are several situations when we may have can go for much simpler form. We hardly have to solve such a complicated equation. In most of the real life situations that we can deal with, can offer several simplifications. Let us just repeat the generalized form. From there we shall be trying to see a few special forms, or instead of special form you can call simpler forms also. So, the generalized heat diffusion equation was dou dou x of kx dou t dou x plus dou dou y of ky dou t dou y dou dou z of kz dou t dou z plus qg dot triple prime is equal to rho c dou t dou t. The first set of simplification that we can have, if we are dealing with an isotropic material. Isotropic means the thermal conductivity is direction independent, that is your kx is equal to ky is equal to kz is equal to k, let us say. Then we can drop the subscript and it becomes k in all the expressions, that is okay. But even simpler situation we get when we consider isotropic material with constant thermal conductivity. As we have seen in the previous lecture, thermal conductivity definitely varies with temperature, but if the temperature range that we are concerned about is not very significant, the variation of thermal conductivity can often be neglected. Then what happens? Now, K, we are talking about an isotropic material, and K is not having any kind of direction dependency and it is constant, then we can take the K out of this. Then the equation now becomes just dou T2 dou x2 plus dou 2t dou y2 dou z2 plus qg dot triple prime upon k plus equal to rho c upon k dou t dou t. Now, what is this rho c upon k, this quantity, or maybe k upon rho c? That is the thermal diffusivity that we introduced in the previous lecture. So, this is just 1 upon alpha, the thermal diffusivity or reciprocal of that in this situation. So, this is a much simpler form and quite often it is much easier to deal with. We can write this in a generalized form also, that is the grad 2 t plus q0 triple prime upon k to be equal to 1 by alpha dou t dou t. That is one common representation. If we are dealing with a situation where we are bothered only about steady state, what do we mean by steady state? You must have encountered this term. in your fluid mechanics. Steady state refers to there is no time variation, there is no time variation. So, if we are talking about steady state equation for isotropic material with constant thermal conductivity, then what happens? The time variation goes off, then your equation becomes just dou 2 T dou x 2 plus dou 2 T dou y 2 plus dou 2 T dou z 2 plus q 0 triple prime upon k is equal to 0. Of course, we are considering steady state plus the assumptions of 1, that is isotropic material with constant thermal conductivity. And if we have suppose unsteady situation, but uniform, that is no variation in the space coordinates or variation with space coordinates. Uniform, while steady refers to no variation in time, uniform refers to no variation in space. So, if we assume uniform plus the assumption number 1, then what we are going to have? In that case, we have 1 upon alpha dou t to be equal to q 0 triple prime upon k, or dou t is equal to prime upon k into alpha, that is k upon rho c, that is equal to q 0 triple prime upon rho c. That is possible when we are talking about a material having extremely high thermal conductivity, so that whatever temperature gradient that is created at a certain location, that immediately vanishes, or the energy is immediately dispersed to the surrounding, so that more or less an uniform temperature profile is maintained. However, with time it keeps on varying, then we can have this situation. And the simplest possible case that we can have, where we are considering an isotropic material, plus we are considering steady state, plus we are considering one dimension. Actually, the consideration steady state that already considers one. Then what we are going to have for one dimensional flow situation, our one dimensional heat transfer situation, if x is the only important temperature, only important directions, then equation becomes something like this, and if k is independent of space, then it is just d2t dx2 is equal to 0. So, a very simple second order ordinary differential equation which can be solved with suitable boundary conditions. So, there are several special forms that we get, though this is the generalized form of the heat diffusion equation, but quite often we may not have to go for such complicated equation, we can have several kind of simplifications and simpler forms. So, whatever scenario you are dealing with, just carefully look what kind of simplifications you can do and accordingly simplify your equation, and if you are lucky you may well end up with very simple equation something like this. Now, whatever may be the situation, you are dealing with either partial differential equations or even the simplest case of 1D steady state heat conduction problem, ordinary differential equation. Now, even when you are dealing with ordinary differential equation like this one, still it is a second order equation, and to solve this mathematically you need to have how many boundary conditions? 2 boundary conditions are required. So, let us quickly check what are the different kinds of boundary condition that you may encounter. We take a very simple situation, the last situation that we talked about, that is one dimensional steady state heat conduction through an isotropic material. Then your corresponding form of the heat diffusion equation reduces to dou 2 T dou x 2 is equal to 0, just like this. Actually, one assumption that I have not written that I should have added here also, that is no heat generation. Heat generation is absent in most of the situations. Very rarely we find any practical application of conduction, like the example of nuclear fissionable material that I have given. There only we can have this significant heat generation, otherwise it can be neglected in most situations. So, the equation that we have written here is one dimensional steady state heat conduction equation with constant properties and no heat generation. Even if we want to solve this, you will be needing two boundary conditions. Why? Because if you solve this, let us write this as ddx of dt dx is equal to 0. So, if you integrate it once with respect to x, we are getting dt dx is equal to some constant c1. If you integrate it once more, then you are going to get Tx is equal to C1x plus C2. So, there are two constants coming into picture, and therefore, we need at least two boundary conditions. So, the first possible kind of boundary condition is known as the Dirichlet boundary condition, or called the boundary condition of the first kind. Boundary condition of the first kind, or Dirichlet boundary condition. Dirichlet boundary condition refers to when the temperature is specified. Actually, the term Dirichlet boundary condition is a very general one. It is applicable to any kind of fluid flow situations. It is a general, the name Dirichlet boundary condition refers to whatever is the variable for which we are looking to get the solution, the magnitude of the variable itself is specified at some boundary. Like you can say some surface temperature, you are solving a heat conduction problem. Let us take a problem like this. We have a surface maintained at some temperature Ts, and we are assigning a long metal rod to this, and we want to know the distribution of this rod through this particular distribution of temperature through this particular rod. I am not talking about the second boundary condition, but the boundary condition at this point can be a Dirichlet boundary condition, because the magnitude of temperature is specified. So, the common form of Dirichlet boundary condition can be written as T at location x equal to some reference value, let us say x equal to 0 in this case. If we start calculating x from here and assign this point as x equal to 0, then at x equal to 0 time t is equal to Ts, which can also be a function of time. So, if Ts is not changing with time, then this is of course a fixed boundary condition. Yes. This kind of boundary condition is very easy to handle. This is not the Dirichlet boundary condition. The boundary condition of the second kind, called the Neumann boundary condition. Neumann boundary condition refers when the temperature gradient is specified, not the value of temperature, rather the temperature gradient is specified at the location that we are looking to identify. Like the same situation, we have a surface and we are assigning a rod to this surface, but this surface is receiving some, say, q dot double prime amount of heat from certain source, maybe solar radiation or maybe from an electrical heater or from some source, it is getting this heat flux. Then what is specified, how we can calculate? The temperature value at the surface is not given. So, this is our x direction and this position is x equal to 0. At x equal to 0, the value of temperature is not given, but what is given is the heat flux, and using conduction, then we can write this q dot double prime at this location x should be equal to the corresponding conduction heat flux, which is minus k into dou t dou x at x equal to 0. This form is called the Neumann boundary condition. It is a very common boundary condition, quite similar to the Dirichlet boundary condition. Quite often you will find problems where you have Dirichlet boundary condition specified at one end and Neumann condition at the other end. A special case we can get where this dou t dou x equal to 0, that is, we are talking about an adiabatic surface through which no heat flux is allowed to pass through. Adiabatic boundary is only a special case of the Neumann boundary condition. And the third one is called the convective or radiative boundary condition. Here let us talk about the other end of this pipe. So, this is the surface through which we are assigning or we are connecting this tube. At this end you may have the temperature specified, or you may have some heat flux specified. Accordingly, we can have a Neumann or Dirichlet counter boundary condition. If the temperature is specified, it is a Dirichlet boundary condition. If the heat flux is specified or it is mentioned to be adiabatic, that is a Neumann boundary condition. But let us say this other end is open to atmosphere. It is open to atmosphere means, if we zoom up this portion, say from this tip, energy is being transferred to the surrounding. Because this portion is open, let us say these portions are insulated, heat is not allowed to pass through the sides, heat is allowed to pass through only through the tip, and the tip is open to surrounding air. And if the temperature of this tip, this face, that is I am talking about this particular face only. If temperature of this face and the surrounding air are different, then there will be convective heat transfer, because air is flowing over this surface, and accordingly if the air temperature is low, that will pick up heat from here. That boundary condition is known as the convective boundary condition. How can we get it? Let us say this location is referred as x equal to L. Now, what will happen? On the left hand side of this x equal to L, that is I am talking about on this side, what is the mode of heat transfer? Mode of heat transfer is conduction. What is the mode of heat transfer here? Mode of heat transfer is convection, and under steady state condition, then these two should balance each other. That is, whatever you have the conduction heat flux on the left hand side, which can be written as minus k dou t dou x at x equal to, let us say, L minus we put to indicate that on left hand side, that should be equal to the convective heat flux acting on the right hand side. And how we write the convective heat flux? That can be written as H into T at x equal to L plus minus T of the surrounding. This condition is known as the convective boundary condition, where we are assigning, or when we are equating the conduction heat flux with the corresponding convective heat flux. In certain cases, instead of convection, we may have radiation. In the same we can write it, the conduction heat flux dou t dou x at x equal to L minus should be equal to the corresponding radiative heat flux. And how we can write the radiative heat flux using a Stephen-Boltzmann condition? It is the emissivity into sigma into T at x equal to L plus to the power 4 minus T infinity to the power 4. Of course, do not forget to convert this T at x equal to L plus and T infinity to the absolute temperatures, because these are all absolute temperatures. So, this way we can easily assign a convective and radiative boundary condition also. These are all very common boundary conditions, and you will encounter numerous heat transfer scenario in this course itself, where we have to use either any one or maybe a combination of 2 or 3 boundary conditions. In fact, the third one that we are talking about, you may find a situation where both convection and radiation going on. Like one diagram we have seen in the previous slide, or not previous slide, in the previous lecture, where we have seen that a surface is receiving energy by radiation, but it is also losing energy by its own emission and convection. If both convective and radiative heat transfers are important, then in that case we have to put all 3 heat flux types of heat fluxes together. That is, on the inside of this surface, that is at x equal to L minus, we have this conduction heat flux that should be equal to the corresponding convective heat flux, and the radiative heat flux. In this case, all 3 modes of heat transfer are coming into picture, but unless the temperature at this x equal to L plus is extremely high, radiation generally is quite insignificant, but convection can be very dominant in several scenarios. So, let us use this idea to solve one exercise problem now. Here the problem is given that the temperature across a 1 meter thick wall at a certain instant of time is given. So, let us say this is our wall, the thickness is starting this as x equal to 0, this is direction x, this is x equal to L, this thickness is given as 1 meter. So, our L is equal to 1 meter. It is given that the temperature distribution is following a quadratic law like this, and the corresponding volumetric heat generation rate is given. So, there is a volumetric heat generation, that is Qg dot triple prime is given as 1 kilowatt per meter cube, and the wall has a cross section area of 10 meter square. So, the cross section area is 10 meter square. You can write AX also to indicate that we are talking about the wall which is having or rather the area which is having normal in the x direction. That is, we are talking about actually this particular area for the wall, which we are not considering for analysis. This is a one dimensional heat conduction scenario that we are talking about. So, heat is getting transferred from one wall to the other wall, and certain informations are given. We have to use this information to estimate the rate of heat transfer from both the faces of the wall, time rate of change of energy storage in the wall, and time rate of temperature change at the mid plane of the wall. So, mid plane refers to something like this, that is the one corresponding to x equal to L by 2, that is 0.5 meter. Certain values are given which I have noted down separately. It is given that A is equal to 900 degree Celsius. It is given that the temperature is in degree Celsius and x is in meter. So, B is given as minus 300. What should be the unit of B? Any term in this equation, all the 4 terms should have the unit of Celsius. Now, B is multiplied with the length scale, then it should be degree Celsius per meter, and C is given as minus 50 degrees C per meter square, and certain properties are also given for the corresponding wall material. Its density is given as 1600 kg per meter cube. Its specific heat is given as C or Cp, whatever you would like to write, 4 kilojoule per kg Kelvin, and thermal conductivity K is written as 40 watt per meter Kelvin. So, these are the set of informations given. We have to estimate first the rate of heat transfer from both the phases of the wall. So, we know that at any location x, the temperature is given as T A plus Bx plus Cx square. Then what will be dt dx? Here we are talking about a 1D scenario, and under steady state we can assume steady state as or at least okay, let us do not consider steady state, because later on we have to calculate the time rate of change of energy. So, space variation of course can be neglected. Then dou T dou x can be written as A, B, C being constant, it can be written as B plus twice of Cx. So, the first part of the problem, we have to calculate the rate of heat transfer from both the phases of the wall. Then rate of heat transfer Q dot from the left phase, that is x equal to 0. How that can be written? Because it is only conduction heat transfer that is happening inside to this. So, it should be equal to minus k into the area at x equal to 0. Okay, we shall be putting that later afterwards. A k A dou T dou x, everything at x equal to 0, that is minus k into the area, both are constant as per the given problem, into dou T dou x is given as B plus 2 Cx at x equal to 0. So, if we calculate the number, this is equal to minus k A, and putting x equal to 0, this just leads to B. So, we have k equal to, in the given problem, k is equal to 40, area is given as 10 meter square, into B is given as minus 300. So, if we combine all these numbers, we are getting something like this. And what is the unit of this quantity? This is the heat transfer rate that we are talking about. So, this is watt, or we can write in a concise form 120 kilowatt. Similarly, Q dot at x equal to L, again it should be equal to minus k A dou T dou x at x equal to L. So, minus k A B plus 2 Cx is equal to L. So, it becomes minus k A B plus 2 Cl equal to minus 40 into 10 into B is minus 300 minus 2 into 50 into L, in this case is equal to 1. So, if we combine all these numbers, I have noted the value, it is coming to be 160 kilowatt. So, from the left phase the rate of heat transfer is 120 kilowatt, and the right phase it is 160 kilowatt. But both of them are coming to be positive. You have to remember, we are talking about heat transfer rate which can have a direction. Here both of them are coming to be positive. What does that indicate? in through both phases the rate of heat transfer is in the positive x direction. So, this is your q dot at x equal to 0, this is the direction. For this case also this is x equal to L, this is the direction for this. So, 120 kilowatt of heat is entering through x equal to 0 via conduction, and 160 kilowatt is leaving by conduction again through the other phase. Now, I have to estimate the rate of heat transfer from, we have to estimate the rate of heat transfer which we have done. Now, I have to calculate the time rate of change of energy storage in the wall. So, you have to calculate the time rate of change of energy storage. If we write the energy balance equation, minus E dot in plus E dot out plus E dot generation is equal to E dot stored, and this is the E dot stored that we have to calculate. So, your rate of energy storage should be equal to, what is our E dot in? Energy can enter only from that x equal to 0 phase, which is 120 kilowatt. So, it is 120 into 10 cube, which is entering. E dot out, that is energy going out through the x equal to L phase, which we have calculated to be 160 kilowatt. So, it is 160 into 10 cube plus energy generation. We have an energy generation in this case, which is given as 1 kilowatt per meter cube. So, it is 1 into 10 cube watt per meter cube. So, you have to multiply this with the volume, because we know that E dot g is equal to q dot g triple prime into dx dy dz. So, how much is the volume? Here we are talking about a wall which is having a thickness of 1 meter, and the area of each of the faces is equal to 10 meter square. So, this is nothing but 1 into 10. So, what we are getting? We have 120 minus 160 plus 10 into 10 cube, that is equal to minus 30 kilowatt. So, the block is actually losing energy, or it's, I should not or I should say that the total energy content of the block is decreasing following this at this particular rate, despite the energy generation. It is receiving energy from one of the phases following at a rate of 120 kilowatt, also 10 kilowatt, at a rate of 10 kilowatt energy is getting generated, but it is losing 160 kilowatt of energy, or at a rate of 160 kilowatt from the other phase. Accordingly, its total energy content is continuously reducing. Now, come to part 3. In part 3, you have to calculate the time rate of temperature change at the mid plane of the wall. Time rate of temperature change at the mid plane of the wall. So, let us go to the heat diffusion equation. The general heat diffusion equation for one dimensional isotropic material, how we can write this? So, we had k d2 dx2 plus qg dot triple prime. We are writing the heat diffusion equation, but it is one dimensional version, assuming an isotropic material, that is with constant k. So, the k has come out and it is one dimension, only x is the direction. So, this should be equal to rho c into dou t, or I should not have written capital D, I should stick to the partial derivative notation, because t in this case is varying both with time and x direction. Accordingly, the time rate of change of temperature at any particular location can be written as k upon rho c into dou 2 dou x2 plus q0 triple prime by rho c. Now, what was the temperature profile that was given in the previous slide? T was given, dou t dou x we calculated, but the second derivative we have not done. We had T as a function of x and t was given as a plus bx plus cx square, which means dou t dou x at any particular location at a particular time can be given as b plus 2 cx, which we have already used. B plus 2 cx we have already used in the first part of the problem. Now, we need the second derivative. So, dou 2 t dou x2 So, the B also cancels out, we are left with twice C, and C being a constant, we can directly put the magnitude to be equal to minus of 100 degree C per meter square. So, we know the magnitude of this quantity. So, if we put it now, K, rho and C all values are given, K is equal to 40, rho is equal to 1600, C equal to 4 kilojoule per kg Kelvin. So, K equal to 40 by 1600 into 4 into 10 cube into dou T T dou x 2, which is minus 100 plus q g dot triple prime. We had q g dot triple prime to be given as equal to 1 kilowatt, that is 1 into 10 cube. Note that I am writing all of the magnitudes in basic SI unit, so that there is no confusion with kilo or mega or any such kind of units. 1600 into 4 into 10 cube. From the top we have just 1 upon 1600 left here, whereas in this case we are left with 1 by 6400. Calculating this quantity is coming to be something like 4.69 into 10 to the power minus 4 degrees C per second. 4.69 into 10 to the power minus 4. It is an extremely small rate, and also you can see that this, though we are supposed to calculate this particular quantity as a mid plane, but actually we are getting this dou t as a fixed number, as a constant number. That means, anywhere in the domain from x equal to 0 to x equal to L, at all the phases, the rate, or at all the planes, the time rate of change of temperature is like this, that is, the temperature is continuously decreasing at all the points. So, that is how we can use a generalized form of the heat diffusion equation in conjunction with the Fourier's law of heat conduction. So, that is where I would like to stop today. We have talked about the generalized heat diffusion equation. This is its version in Cartesian coordinate that we have derived. Then a few special forms, like for isotropic materials, for steady state, for uniform materials, or the very special case of one dimensional steady state heat conduction with constant properties as zero heat generation, that was developed. Then we talked about the boundary conditions. So, that is it for the day. In the next class, I shall be developing the equations in cylindrical and spherical coordinate as well, and then we shall be seeing the applications of those equations through quite a few numerical examples. Till then, please revise this lecture and try to solve a few more numerals sticking to the Cartesian coordinate system. Thank you very much.